In this video, we're going to learn about radiation. Radiation is the emission or transmission of energy in the form of waves or particles. It is known that a number of isotopes from certain atoms actually emit radiation. Let's look at the example that we have on the right side of the slide. Carbon has different isotopes, which include carbon-12, carbon-13, and carbon-14. As we can observe, carbon-12 is stable, carbon-13 is also stable, but carbon-14 is not only unstable, but is radioactive, which that means that out of the carbon isotopes, carbon-14 is a radioisotope because it emits nuclear radiation. Carbon-14 has a radioactive nucleus, meaning that it can undergo spontaneous changes and emit energy in the form of radiation. There are many types of radiation, but in this course, you need to be familiar with at least 3 of them, which include alpha particles. This is the particle that makes up alpha rays, and it has a positive electrical charge. Next, we have beta particles, which is the particle that makes up beta rays, and it has a negative electrical charge. Lastly, we have gamma rays, which are a high energy ray that it is like an X-ray, but it is uncharged. Exposure to radiation may be happening even in doing everyday activities. The image that we have on the right side of the slides represents a visual hierarchy of radiation exposure levels measured in millisieverts, which is the unit of measurement for radiation dosage. And it ranges from negligible doses to lethal amounts. At the bottom of the graph, we can see resources of minimal exposure, which include eating a banana or even taking a 14-hour flight. As we move towards the top, we can look at the increasing severity of radiation effects as exposure increases. And we can observe that at 1,000 millisieverts, this can cause humans to be sick, and the effects of it is to cause nausea, and vomiting. There's different ways to detect radiation. Here in slide 13, we have different instrumentation for the detection of radiation. The first one that we have is a Geiger-Müller tube. In other words, a Geiger counter. This is the tube for the Geiger counter, and then you can see the readings in the box. This radiation detection device operates on the principle that ions are going to form when radiation passes through a tube filled with low pressure. Next, we have a scintillation counter. A scintillation counter works by operating on the principle that certain substances give off light when struck by radiation. And lastly, let's talk about one that is used in the medical setting, which is a film batch. And we can see that this worker has a film batch specifically in her hands. When it comes to a film batch, we can see that how they work is like an old school photographic film. Inside of the batch, there is a piece of black and white film, and when there's exposure to radiation, the film itself will darken. One of the things that I want you to also be aware that radiation has also been utilized in the treatment of some cancers. Radiation therapy works in different ways. One of the main ways in which radiation therapy targets cancer cells specifically is by targeting a specific biomolecule that is inside a cell that is called DNA. Radiation damages those DNA molecules inside of those cancer cells. And because DNA is going to be the molecule that sends the message for growth and division, once the DNA is damaged, then cancer cells specifically are going to be prevented from growing and from dividing. If cancer cells are specifically damaged, they are less able to repair this damage. So once radiation therapy has occurred, understand that the cancer cells are going to die off over time. Radiation therapy can also have gradual effects. It can take days, it can take weeks before the cancer cells die. But the thing is that once radiation therapy has occurred, those cancer cells may continue to die for weeks and months after the therapy has occurred. As we can see on the image on figure 2.15, alpha and beta particle emitters are frequently used in radiation therapy to treat cancer cells. In table 2.7, we can see an example of a therapy for cancer treatment. Specifically, here we have cobalt-60, which its emission includes beta and gamma rays. One more interesting thing that is also illustrated in table 2.7 is the half-life of that isotope. Half-life refers to the time required for a quantity of substance to reduce to half of its initial value. And as you can see, for cobalt-60, that's going to be 5.3 years. Additionally, I want you to observe that not only isotopes or radioisotopes have been utilized for the treatment of cancer. Another example that we have specifically in this table is the illustration of how radioisotopes can also be utilized in diagnosis. And we have many examples of radioisotopes that can be utilized in order to scan the human body and detect organs or tissues that are affected. Radiation exposure can affect our health. So it is important to understand how, through shielding, we can minimize the exposure to radiation. In table 2.6, we have the penetrating abilities of alpha, beta, and gamma rays. We can observe that specifically when it comes through traveling, alpha, beta, and gamma rays will be able to travel through air. When it comes to the depth of the penetration of these particles into tissue, we can observe that there are a few measurements in millimeters, except in gamma, which is centimeters, of how these particles can penetrate. Lastly, in here, we can see that if these particles are shielded by lead, specifically, we can see how all of a sudden that penetration is reduced. What that means is that there are some materials that can be utilized as shield in order to minimize exposures to these different types of radiation. So when we look at figure 2.22, we can observe that alpha particles can be shielded by newspaper, beta particles can be shielded by plexiglass, and gamma rays can be shielded by lead. So if we observe the image that we have here in the bottom right corner of the slide. This explains why at times when there's certain procedures or x-rays or gamma radiation needs to be present in a treatment or in a scan, the use of very dense materials such as leads are utilized in order to provide protections for other organs that don't need to be exposed. So in this person here, we can observe how this jacket that is in blue, it is utilized to shield specifically the rays and only target the area that needs to be visualized. At the end of the day, understand that alpha and beta rays are going to be the easiest to stop via shielding.